Yeah, good morning, everyone. My name is Michael Kastner or Michael Kastner, depending on the kind of pronunciation I'm getting, depending on the country. Well, first, welcome also from my side to the school. I'm looking forward to, well, for me, it's only going to be the first 5 days, so the first week of the school that I'll be able to participate. And so what I've prepared goes under the name Quantum Systems with Long-Range Interactions. But today's lecture, especially because it's the very first lecture of the school, I will not so much focus on the quantum part, but I will try to give a sort of more general introduction on the field of long-range systems. And of course, it's a vague term, and I try to give some meaning to it by explaining some historics. So I'll try to give a little bit of the history of the field and an emphasis why people have found it particularly interesting in the past decade or two, I would say. So that is the plan for today. And then in the following lecture, we'll get lectures from tomorrow on, we'll get more into details. So there will be hardly any equations today, but we'll get to some proper physics, I promise, in the coming days. So yeah, so as a general remark, I'll now start and give you my definition of what I mean by long range. And the warning at this point is that there is no general agreement on the use of the term. This depends a lot on the community, on the people, well, what is the field of people working in? And there is a reason for that. So you may think that not having a uniquely agreed on definition may be a weak point, but it can also be seen as a strong point. It means that you can you can in some way choose a definition that makes your topic interesting, that you select the right definition for finding interesting physics. Whereas a rigid definition maybe will not be able to do that. Anyway, I'll tell you what I'm going to use and make some comments what is done in different fields. So, and okay, just I'll just have to get mentally used to how I'm going to use this. So before I write down the definition, I'll give you a sketch of what I usually have in mind as a system when I'll be talking about quantum systems with long-range interactions. The reason is that these definitions, they can be applied much more broadly. They will work for classical as well as quantum systems, lattice models, or continuum models. But for the purpose of my talk, I'll be usually thinking of something, and I'll use the simplest examples usually that I can work with. So I'll usually think of lattice systems, and whenever there's no reason to go to higher dimension, I will give examples that are one-dimensional, just for simplicity, to explain the concepts in the easiest possible way. So I'll think of something like a quantum spin chain, for example. This is the lattice. At each of these sides, there is a quantum degree of freedom, say a spin 1/2 sitting, and then with this usual sketch, then these links here would indicate nearest neighbor interactions between the lattice sides. And then the simple thing that you do in long range, you say, well, it's not only nearest neighbor interactions, but I will also think of something that extends, say, over next nearest neighbors, and maybe I also have third neighbors, and so on. And as I said, usually what I'm be looking at, it will be either quantum spin models or fermions or bosons on a lattice again. I'll get into more details later, but this is just I'll not so much talk about continuum models, but this is more what I have in mind. Okay, so on such a either spin lattice or fermionic or bosonic lattice, then the two ingredients that I need for defining long range, first I need a notion of distance, which will usually be just the distance on the lattice. So if this my lattice I and I plus 1, then the usually distance I between I and I plus 1, of course, will be 1. That's quite simple. And then I need some interaction potential that I will be calling V, usually between the sides, and the qualities of this potential will be what I use for the definition of long range. So now, no, the wrong way. Okay. Okay, so we have already some information on here. Good. Right. Yeah, the definition, let's start with the opposite of what we're doing. Let's start with short range. And this for me will be everything that is of finite range. Finite range could be nearest neighbor, like the one example that I started with. So something like for all pairs of i's and j's, no, sorry, it's say I take an interaction potential between the sides v, I, and j, and if this is 0 for all ij, where the distance ij is greater than some delta, this is what I will be calling finite range. So in a sketch, let's put a sketch here on the other side. If this is my lattice here, so there's some distance here, and this is the interaction strength, then it will be the interaction with distance 1 will have some value, and from some value onwards, it will go down to 0. So anything like this would be my finite range interaction. Quite simple. And well, long range will be algebraically decaying. So the potential, depending on these lattice sides I and j, or the absolute value of it, will be proportional to some constant, and then the distance between I and j to some power minus alpha. So power law decaying interaction, this will be my definition here. And so yeah, and this alpha will be some exponent that is larger or equal to 0. So just to plot this in here as well, this could be, if I start here in the same way, but this here goes on and on and on like this as a power law, then this would be my long range example. And just to go to the extreme cases, if this exponent alpha is 0, then of course there's no distance dependence in here. So alpha equals 0 would correspond to this case here, up here, constant, not decaying with the interaction. And the other extreme case would be if this alpha becomes very large. So if you can think of this here in the limit alpha to infinity, then essentially distance 1 to minus infinity will still be 1, but all the others will be 0. So in the limit alpha to infinity, you will stay here at the 1, and then it will decay super quickly to 0. And in the actual limit, alpha going to infinity, you recover nearest neighbor. Interactions. So this is essentially the link from infinite range to finite range models by changing this exponent alpha. This will be the whole question of the game. What exponents alpha are interesting? Which ones can we find in nature or in experiments? And this is the kind of this will be the alpha will be something like the main parameter that is also be investigated No. Okay, just a few remarks on generalizations. First remark, you may wonder between short range and long range. What about something that is extending infinitely but is decaying faster than the power law? So what about an exponential decay? The exponential decaying interactions are usually, I would assign to the short range interactions. And there's two reasons for that. Firstly, the physics turns out to be very much that of finite range interactions when the decay is exponentially decaying. And mathematically speaking, there are, for many results, if you show something for all kinds of finite ranges, you have some sort of convergence to the behavior of an exponential decay. So also for mathematical proofs, it turns out to be usually the same. And the technique of proof would be show that for any finite range, something holds, and then the extension to infinite range will give you usually the same results. So, and the generalization that can also easily be done is, how do I call this, beyond pair interactions. So when you have proper many, say 3-body interactions, 4-body interactions, these definitions can easily be adjusted as well. There's not much really of a difference. And yeah, and then the third category I want to introduce, because it's used quite a lot in the literature as well, is strong long range interactions. And this is like long range, but when the exponent alpha is larger than or larger equal, this doesn't make a difference really, than the dimensionality of the system, like the dimension of the lattice. So for the 1D spin chain I was showing, if alpha is larger, smaller than D, then, well, usually we don't go below 0. So in this range here, this is often given an extra name, strong long-range interaction. The reason simply being that in that regime, long-range effects, like phenomena, are very often more pronounced. And this is a regime where one more easily finds differences to short-range interacting systems. And this is why this has received proper attention and got its own name, strong long-range interaction, to distinguish this case. All right, so this is the wording that I'll be using, and just a few comments on how this is used in the literature. Let me just finish the sentence before. And so if you look into the classical literature, like classical long-range systems, very often only this part here, what I call strong long-range, is called strong long-range at all, and this will be assigned to short-range. You can argue that this is a good idea or not, but it really, the warning at this point is only, if you look in the literature, don't trust that people are using exactly these definitions. This may change. Yes, please, you wanted to ask. The dimension of the lattice. So for the example that I was showing is a 1D lattice, or whatever the dimension is. Why the dimension is the cutoff? Yeah, there is a reason, but you get this reason, and we'll get to this later, when you consider the physics, especially the equilibrium physics of models. You will find a strong difference in the behavior of systems when with alpha smaller than the dimension and alpha larger than the dimension. So the definition is really inspired, if you want, by the physics that you get. This is what, when I made a very brief remark at the beginning that there may be good reasons for not having that one fixed definition of something in a field, because it really depends on what you're looking at, what you're interested in. And if it turns out that below this threshold, you find physics very different from above this threshold, this may be a good definition for this subfield. But if it's different, if you're looking at other things and there's no such distinction, then you may wonder. So it's really, sometimes these definitions are not 100% well used in the same field for good reasons. So it's not, I'm trying to make the point that it's not always a weak point to have this ambiguity in definitions. But yeah, with these words, I hope it would be clear, and we'll see a strong difference in physics behavior for systems with alpha smaller and alpha larger than the dimensions. Right. So with this definition done, let's get to the relevance of long-range interactions in physics. Another question, please. Well, so I'm not even decided myself whether I won't include the alpha equals d to the strong long range or not. In reality, the reason for or that at alpha equals d, you will even have a special case where things have to be considered separately because the physics may be again different at exactly that point. So let's stick to my notes. So I see in my notes I use this here as an smaller than d, but alpha equals d is really a special case where, for example, if you look at phase transitions or quantum phase transitions of that models, you will have special behavior at that exact point. So again, yeah. Okay, when maybe can I first ask, how many of you have worked or have a project that involves long-range interactions? One. Okay, so it's a few. Okay. So just to get an idea what the background of the audience is a little bit. So when you think of systems with long-range interactions, it may depend very much on your own background, whether you would think, well, long-range interactions, well, this is very particular or peculiar, but don't we have this all the time? So the point I'm trying to make, if you look at the physics, at fundamental physics, like the fundamental forces that we have in physics, electromagnetism, or say Coulomb potential, you would say, well, that's long range interactions. In lower dimensions, it's even strong long range. If you have, boundary, no, sorry, so that's long range interactions. If you have gravity, you would say, the gravitational potential goes with 1 over the distance, so that's strong long range again. So it seems like that the main physics that we're having is long range. So what's so special about it? And I want to give this as a contrast that what I have in mind for these lectures and what is very often looked at in the field of long range interacting systems is looking at models from condensed matter, which are usually very short range. Usually in condensed matter, you have nearest neighbor models or next nearest neighbor models, or you have short range models, and looking at long range variants of these models. So just the distinction, fundamental physics may be long range, but this is not what we're looking at, but we're looking at many body physics, many particle models, where very often, instead of the usual condensed matter short range interactions, we'll be looking at long range. So just as a quick reminder, why is so much of this condensed matter physics short range? Well, that is the effect of screening. So in condensed matter, you have electrons and protons usually, and so there's positive and negative charges, and there will be screening effects that lead to this short range interactions. If you haven't encountered this, so Debye-Hückel theory is one thing where this is really derived, and you find that what formerly was your described by a Poisson equation with a solution that is power law decaying, like strong long range, that this turns into something that is exponentially decaying with distance, and then you get to short range models. In gravitational physics, we do not have screening. So for the simple reason that there are no negative masses. So the screening effect in solids comes from the presence of positive and negative charges. Whereas in gravity now we have only positive masses, so there is no screening effects. And so this brings us to a class of systems where long-range interactions are pretty much always present and of relevance. And so we'll get to a little historical overview of the field, and because of that, the strong long-range interactions essentially came into being as a topic in the field of gravity as well. So now, so definition should have been my section 1. So let's continue with 2, which is called a historical overview. So the goal of this section is, well, to give you a little bit of an idea what has happened in the past decades, how the field came into being, why people got interested in the topic, and what exactly it was that a decade or a bit more ago gave a particular boost to the field of quantum long-range systems. And so the hope is that by starting the whole lectures with this historical overview, you'll get an appreciation why people found certain questions interesting at some point, but also why these questions have kind of been neglected in earlier years. So with this definition of short and long range that I gave you, then you may first think, well, but haven't I done long range systems in my physics courses all the time? And of course you have. So if you look at few body systems, then the Coulomb screening that I was mentioning, like many positive and negative charges that lead to screening effects, you don't really see this if you have a few body system. Say, think just of a hydrogen atom. And this is something that, of course, you did in your class at university. And then the hydrogen atom, this is a long-range interacting system. You have a Coulomb potential. So but because you always have this in few body systems, there's no one is calling this long-range system, because that is the fundamental interactions that we have, and there's no need of making a distinction. So it's just we have looked at long range all the time, but here it's not particularly relevant. So only when we move on to many body systems, we get to what I was briefly mentioning before, the fact that in many of those many body systems, screening effects let us ignore the long range interaction, or they're not relevant, and we get to short range. But this is different in the case of gravitational models, and this is gravitational systems. And this is historically also where this question of long-range many-body systems, which will be the topic of our lectures, started. So, as I mentioned, there's no negative masses. And therefore, no screening. So no short-range theories apply, and one has to use the proper long-range potentials when doing physics here. And so some of the central problems in astrophysics. So this is, of course, astrophysics is essentially many-body systems with gravitational interactions. So this has been a very active field from the early days of physics. This is also what motivated, of course, the very early investigations of Newton and Kepler and so on. But later on, as well, not as a many-body problem, and later on as a many-body problem by, well, Eddington and Chandrasekhar are important names here. But I'll get to some observation that became very relevant for the field, and that is that of negative specific heats. So the specific heat, how the energy content of a system changes with changes of the temperature and vice versa, is something that was observed in gravitational systems. And I think early accounts are by a guy named Enden from 1907. And the observation was, the usual belief from statistical physics, which was in its early days at that time, was that the specific heat is a non-negative quantity. And now observations and theories from gravitational physics led to the observation that you find systems, gravitational systems, where specific heat can be negative. And this remained a puzzle for quite some time. And I'm now going quickly through some historical remarks and make a jump from 1907 to 1970, when a theoretical or mathematical physicist named Thirring came up with the first explanation of how it can be possible to have negative specific heats. And this was a very influential work for the starting of the field of classical long-range interacting systems. And his observation was that specific heat is usually proved in textbooks to be a positive quantity, and you'll find this in your statistics and thermodynamic textbooks by using the canonical ensemble from statistical mechanics. And then in some other chapter of your statistical physics books, you'll find that there's equivalence of ensembles. So canonical ensemble and microcanonical ensemble will give you the same result in the system, in the limit of large system sizes. And maybe somewhere hidden in your textbook, you find that this proof of the equivalence needs short-range interactions as a requirement. Or maybe in some textbooks you won't find it. At least it was so implicit in there, but not really spelled out, that people were confused at the time, and that these negative specific heats came as a surprise. And Thirring in this 1970 work clarified the situation by pointing out that statistical ensembles can be inequivalent, and it will be a topic later on in one of my lectures here as well, and pointing out that long-range interactions are the main reason for that. So I would say with this work, the highlight of highlighting the fact that long-range makes a difference was, to my knowledge, pointed out for the first time. And again, this is, of course, in this context of many-body systems that I'm looking at here. And right. Yeah, triggered by Thirring's observations, then, well, it still took quite a while after this realization to trigger an effort into we're going away from gravitational systems and saying, well, if long range makes a difference, maybe this is a topic in itself to explore. And this then first happened for the statistical physics of, well, yeah, well, it's a classical long range systems. So the shift in perspective triggered by this work of Turing to a large extent was to say, well, if we can find different physics effects here, why don't we go away from, say, gravitational models and the physics of gravity and consider this as a field of its own, but just asking, well, what happens if I take some statistical model, my favorite statistical model, whatever the Ising model, and I assign long-range interactions to it, and just inquire what are the differences, what can I found, and which results that are usually taken for granted in statistical mechanics have a chance of being different and leading to new physics. And so to some extent, the goal of this endeavor was find or map out, say, limitations and conditions of StatMech. So people were inquiring, well, this is for statistical mechanics, of course, trying to understand when does statistical mechanics maybe run into problems, statistical mechanics as we have usually done it before with short-range interactions. What are the limitations? What are the conditions that I really need to derive the usual results of statistical physics? And then at this point, I want to give a lot of credit for this field to one of the organizers of this school who unfortunately could not be here. So this field, this aspect of the field has then strongly been influenced by a model that goes under the name of HMF. And you'll hear in other lectures, not by me, a lot more about this model, I assume. So this abbreviation is for Hamiltonian mean field model. And if I'm not mistaken, it was first introduced by a guy named Anthony, and who I believe was his supervisor at the time, Stefano Ruffo, and this is the person who should have been here for the school as well, but unfortunately could not come. I assume you'll be talking about HMF physics at some point in your talk, maybe, yeah? I'll still write down the Hamiltonian and give you a quick idea of just one result that I find particularly remarkable, simply because we'll see something quite related in quantum systems later on. So what is this? This is just a model where of classical degrees of freedom with some momenta, pi squared over 2m, and an interaction term. And the spatial variables, if you want, are these angles, theta I and theta j. So what do we have here? There's two ways of looking at this model. Okay, so these are angular variables, so they go from, say, 0 to 2 pi. And depending on the angle, there will be some, if you want, spin-like interactions between these. So you can think of this being a model on a lattice, where at each lattice side, you have a classical rotor characterized by an angle. I draw them like spins, but I mean, so these are rotors in the plane, and they interact with each other with these cosine functions, but independently of the distance of I and j. So this is something like a mean field version of spin interaction here. Well, of rotors interacting and with these momenta, or you can draw the model in a very similar way. If you say you think of masses on a circle, and all masses interact with each other, and the strength of the potential is been given by this cosine. Why is that interesting? This link, these two representations, because this has some ideas of a model of gravity, and there will be a clustering phase transitions of these in this model of these masses clumping together or not. But this other representation here has the flavor of a spin system, of a spin lattice system, where you could also go away from this infinite range interaction here and introduce a distance dependence in here. So I think it's a very beautiful model. Well, firstly because of its kind of simplicity. It's still quite complicated to treat with, but it brings us from gravity to lattice spin models, which is what I'll be going into much more in these lectures. Anyway, for this field of statistical physics of long-range interactions, this model had a huge impact and received lots of attention. And there were interesting results in equilibrium and non-equilibrium. And I just want to give you a flavor of what people found interesting, and we'll find similar effects in quantum systems then later on. Maybe my favorite observation from this field is, say, the observation of specific long-range physics out of equilibrium. And I want to introduce this because we'll see something very similar in quantum systems. But if you plot time here of some system, and I'll not go into the details, I'll just tell you there's some observable that of such a system you'll be looking at. You prepare it in some initial state that I won't go into what it is. And you do some numerical experiment starting at some initial state where this quantity has some value, and you observe what it's doing. And do a very simple plot. The reality looks a little bit different. You'll stay around the initial value for some time. So this is a logarithmic time scale. And then the system will equilibrate at some point and go to some value. So let's say this is the equilibrium value here. And then you make the system twice as large and repeat the experiment. And you find behavior that is similar, but the time scale will be quite a bit longer. This is Hamiltonian dynamics, yes. Yeah. And you make the system even larger, and you find something like this. In a real numerical experiment, this does not look as clearly like this, but the observation that equilibration timescales scale with the system size is something that I find intriguing. It has lots of implications for physics, and it comes in it gets an even and yet another flavor in quantum systems, as we'll see later on. These observations of equilibrium physics of these systems with non-equivalence of ensembles, and the non-equilibrium physics here of, say, timescales that scale with the system size and so on, have given us so many interesting physics that people got quite interested in the field overall and said, there's something to be found and some interesting physics to discuss. Yes, and the thermodynamic limit with a fine print that it may depend on the order of in which you're doing things, as always when looking at a thermodynamic limit. But if you continue this, you would say, well, I get stuck here in this point at this value, and there's sometimes assigned the name of a quasi-stationary state to that here, or pre-thermalization, I think, is a very similar term that is sometimes used but usually the scaling of the timescales is not included in pre-thermalization, which is more used on the quantum side. Question?
Or a single real-time?
Sorry.
So these observables, they are ensemble average or from a single real-time?
So I think I want to leave the topic mostly to so it is more complicated because these numerical experiments are done for a set of randomly drawn initial states, but from a certain subclass. And so you say a subclass of initial states that is easy to parameterize in some way, and then you draw randomly from this subset of initial states, and then do an average over these initial states, and then you get plots like this. I'll show you a quantum equivalent of that in some of the later lectures, and there it will be much clearer because there's no average to be taken except the quantum expectation value, but no ensemble averages. Yeah, so just to label this, so here we have systems. These plots correspond to different system sizes, N1, N2, N3. And there's N1 smaller than N2, smaller than N3. Look, so at the moment, I'm reporting this not as a general statement that this is true for all long-range systems, and I wouldn't believe that it is. So what I'm trying to do here, and so what the upshot of this is only meant to be, people started with Tiring's observation of non-equivalence of ensembles, looked at these models from a different point of view, and found, oh, the physics seems to be much richer than we anticipated. And it's really only in that spirit. So I'm not claiming that this type of behavior exactly holds true for all long-range systems. Yeah. So I mean, I may be spoiling my results from later on, but for example, for quantum systems, we'll see in some way that the timescales will do the opposite. So they'll make the dynamics faster and faster. So there's not this one clear-cut behavior. Well, long-range systems do this or do that. But there is a richness that can be found by introducing long range compared to short range. That's the message here. Yeah.
This is out of equilibrium dynamics. You say this is some
You're asking about the word out or non-equilibrium physics or dynamicals? Yeah. This is a Hamiltonian system. So you may call it just dynamical system. So this is just time. Taking initial states using Hamilton's equations for time evolution and time evolving states. So I know that with the state out of equilibrium, especially in quantum physics, there's usually this notion of stochastic dynamics associated with it, which, yeah, I would say for me, usually non-equilibrium physics is, I would say it's broader than that. I usually use that word by saying, well, we are not in equilibrium and we're trying to do something like a statistical theory, but I would not necessarily require stochastic dynamics to call it non-equilibrium physics. But this is a choice of words. Yeah. I agree that in classical physics, when you say non-equilibrium, people would think stochastic. Yeah. So with this result, where are we at right now? So these works started in the 90s, early 1990s, I would say. And then the interest was mostly in classical systems at the time. And this changed quite a bit later. So where we got to quantum long-range systems. And you may find maybe a few works that are earlier than 2010, but this is roughly the time where the number of works that came out in this field started to increase. So let's say roughly in 2010. And the reason for that interest was, I would say, emerging of two fields. So what happened on the statistical physics side, the one that I just described to you, people were well, after many years, I would say, starting to go more beyond this HMF model, which had dominated the field for quite some time. And people were on the stat phys side were looking at quantum models. So I would say the stat phys was going slowly in a quantum direction as well. But then on the other side, there came up experimental realizations. So experiments of quantum long-range systems became available in the lab. And this, of course, gave a huge boost to the field, where suddenly you would say there was, especially on the classical side, there was a lot of it was academic interest. Like, we're interested in statistical physics, we want to explore its boundaries. What can be put into this framework of statistical mechanics and what can't? But it was not that people were really, or to only a small extent, collaborating with experimentalists and so on. And then experiments, and I'll talk about them in, well, probably in tomorrow's lectures, came up where people have long-range interacting many-body systems in the lab with lots of knobs, what to do with them, initial states to prepare, changing interactions, and so on. And this gave a huge boost to the field. You have a question? I do believe that yes, but I'm one of the less competent people to answer this in this room, and I think there's much more competent people here in the room on this. But I mean, if I'm not mistaken, this HMF model will play a central role in your lectures. Yes. So maybe we just maybe I forward your question to. Okay. Yeah. Another question, please. Yeah. In the lab, to my knowledge, no. So there were the astrophysical observations, but this is of course not a lab experiment. And people had quite a hard time on the classical side finding experimental realizations. So there were a few experimental systems where you can say, well, after some steps of modeling, you end up with something that is at least similar or to this HMF model, for example. I think free electron lasers were discussed at this point, but I know very little about this, so I couldn't explain this to you. But there wasn't really the experiment where you say, now I have this kind of whatever crystal in the lab that has these properties and can be modeled by such a classical long-range system, and I can do experiments with it. So this is why there's pretty much no experimental verifications on the classical side, but they came in on the quantum side with this field. Yeah, so these two coming together, and of course you can imagine once people have something in the lab, and these experiments are also closely linked to the efforts of quantum simulation and quantum computation, which anyway is a field that has seen a massive boost. Then this, of course, also raised the interest in the stat phys side of long-range interacting systems. And these two together then led to what will be the main topic of my lectures. Yeah, so with this, I think you should now have an idea what got people into this field, general interest in what can and cannot be put into statistical mechanics, and the interest in experiments with long-range interacting quantum systems, and how these two can be brought together. And so before I start, I'll give you the two general references for this topic, that for the quantum long-range systems that exist. There's two reviews available, well, 1.5, I would say. So one is a proper review, and the other is already a bit more specialized. And so my selection of topics is different from what is in the review, but there will be a strong overlap. And if you just want to continue reading on the topics that I'll be presenting, this always can be a good starting point. And when I start with my proper lectures, I'll also include some more specialized references on the way. But the general ones is a review by Niccolò De Fenu and collaborators. I'll not list them all here. And the name is Long-Range Interacting Quantum Systems. And it was published in Reviews of Modern Physics. And it's also fairly recent, so it's pretty much up to date. Yeah, the second one is, as I said, quite a bit more specialized. It also has Niccolò De Fenu as a first author. So he's the one actively reviewing the field as well. And I'll not write the title here, but this is a physics report. And that is from this year. By the way, can you read my writing in the back? Is that all right? Okay, good. So this was my general introduction, and I hope you got an idea what people find interesting in the field, and applies obviously also to me, what I found interesting in the field, why I got into that. And so now I'm ready to start with the proper material of these lectures. Before we go there, are there any questions right now? Anything on the general side that you would like to ask? Okay, then I think, yeah, let me tell you what my plan is. So the rest of today's lecture, I want to use to talk about something that I'm not the biggest expert on in the world, but I believe that it's useful for you to get a feeling for the field. I'll be talking about experimental realizations that gave such a huge boost to the field of quantum long-range interactions. And I'm, as you may have guessed, I'm not an experimentalist. I'm a theoretical physicist. But I have collaborated with a number of experimentalists, and especially with one experimental group, I also really went there and made an effort and spent a couple of days in the lab to really get a feeling of this experiment. I'm still surprised they let me even touch some of the knobs and try to do some stuff, but it was quite an experience for me. But just as a disclaimer, I'm far from an expert in that field, but I hope that I learned enough about it to give you a flavor what in these experiments can be achieved or what can't be achieved and why, how. And of course, I'll give you a theoretician's flavor, trying to tell you where these long-range interactions come from. So that's the plan for now. So I think this I can. So part 3 is what I call synthetic quantum systems. Yeah, this word synthetic here, of course, like is a vague notion as well. I mean, there's so many man-made, like not naturally occurring systems that we have. Many materials are, but I don't mean like just materials created in some way. But this is a word that is sometimes used for experiments that go under the labels of cold atoms, trapped ions, and so on, where people have in a very controlled fashion quantum systems in the lab that they assemble essentially to have similarities with solids, but these are not solid. These are trapped gases essentially. And so think of these types of systems, and this is what I will be talking about here. So how does it? Well, where does the interest in these systems come from? I'm sure you may be aware that when people talk about quantum technologies, that there's 4 columns of quantum technology that are usually mentioned that are important for the technology of the future, and this would be quantum computation, quantum simulation, quantum communication, and quantum sensing. Yeah, so this is sometimes hailed as the 4 columns of quantum technology. Why do I mention this? The first 2, quantum computation and quantum simulation, have been based mainly on the same kinds of platforms that people are using to looking into these. And so people started many different, say, branches of experiments that they try to use for quantum computation and quantum simulations. And it's usually having quantum degrees like atoms in some very controlled environment, cooled down to very low temperatures, trapped to have some control over them, maybe be able to place them at different positions at will. And these experiments have been around in the labs for now 25 years, roughly, or experimental platforms that are used for these purposes. And it turned out that, and these 2, especially because quantum computation people have ideas from classical computation with this, which is solid state based, and they have solid-like systems, but in a very controlled way in the lab. So these two systems, these two tasks here naturally led to cold atomic systems mostly. Which are similar in some way to condensed matter systems. And this will be our starting point, because people try to construct systems that are very cold, very controlled, and similar to condensed matter systems, but it turned out that in some situations these systems showed long-range interactions. And then people started getting interesting to it. It may be a negative and unwanted side effect in some cases, but they also said, well, maybe it's something we can do something interesting with it. So essentially, when I said that these two fields came together, it was essentially by luck, I would say, that long-range interactions popped up and said, well, look, here's something that we didn't have usually. Now, physicists, you should learn about it and study this. So what are the primary examples? Of such systems where we do have long-range interactions. So it's polar atoms or molecules. So when these have a significant dipole moment, for example, and then they can be experimentally, to control them, they can be either in traps or in what is called optical lattices, or in tweezer arrays. This is now a lot of name dropping at the moment. I'll just, for those of you who have heard of these kind of platform, I'll give a short overview where we are at, and then I'll select one and give you a lot more details about this. So, this essentially means there's different ways of, we want a lot of control about these experiments. There's different ways of controlling it, but the main ingredients are atoms, molecules that are polar or that are highly excited to some Rydberg states, where we again get something like a large dipole moment. And another platform is trapped ion arrays. So when it's not neutral atoms like in these cases, but ions. And so I have worked quite a bit with trapped ion experimentalists. This is why, for me, it's the natural choice to tell you a bit more about this platform. These platforms, I would put the field like this. There's not the general technique or the general idea that is used in all these cold atom or trapped ion platforms, but it's really sometimes a field where every lab, every scientist creates his own systems with his own knobs and the own, in some way. When you know a lot about trapped ion systems, you may still have no idea how a Rydberg platform works and the other way around. So these are very specific fields and topics where you have to go into one. But I believe still that the idea of seeing once how long-range interactions arise and what in principle is done in such an experiment may help you to just appreciate what people have in the lab and what can be done. So that's the plan for now. I'll tell you a little bit of, in a schematic way, what people do with trapped ions and where the long-range interactions arise from. And so that's the plan for now. So section 3.1 will be trapped ion realizations of quantum spin systems. Right. So how do I set the pager? No. Ah. Okay, so there's some delay with the. All right. I know works. So as I told you, for me as a theorist, this will be a very schematic view on what is happening and what people are doing. And I'll just tell you in a few sentences what people get, but I will not be able to tell you where which laser exactly is placed to achieve what is achieved in these experiments, but just what the idea is. So this is one example of an ion trap. So an ion trap is an array of magnetic and electric fields that is adjusted in such a way that there will be a minimum of a potential for trapping ions somewhere in the middle. So these by an array of, well, these are big magnets and then plus electric fields. This is an example of a penning trap, which has static magnetic and electric fields. There's other traps that use oscillating fields. And the arrangement of magnetic and electric fields is such that there will be flat, like pancake-shaped potential minima where the ions then all assemble. So the ions are trapped here in this flat kind of circular area around here. And then what these ions do, because it's one species of ions, they are all positively charged in this case. They will repel each other. And by repulsion, they will try to be, of course, as far away from each other as possible. And they'll arrange themselves without external forces, if you want, into regular, well, an almost regular triangular lattice that you see here. Of course, on the boundaries, there's some boundary effects here that disturb this regularity, but otherwise there's, well, to good approximation, there's a triangular lattice in which these ions arrange themselves in a 2D plane. And then the experiment is constructed such that there's lots of ways of shining other laser beams and so on onto these atoms to do things with them. Okay, now so this actually here is an actual picture taken, like a photograph of the experiment. So this is a fluorescence image, and the length scale you see here is the distance between atoms is in the range between tens and hundreds of micrometers. And the length scale will be important. I mean, for now, compare this to, it looks a bit like a regular lattice like that you have in a solid, but the difference is, of course, that the length scale is completely different. I mean, there's, what is it, 5 orders of magnitude difference to the usual angstrom distance that you have in crystals. And why is that? Does this make a big difference? Firstly, you'll have better access, so you can have even the chance of addressing with a laser beam a single atom and say exciting it or de-exciting it. So it gives a lot more control. But it also may have the advantage that initially, when atoms are that far apart, they will not really interact with each other because they're so far apart. But we'll get to this in a second. So the title of the section is Trapped Ion Realizations of Quantum Spin Systems. So where's the spin? And spin in this context here is really a name for a two-level quantum system. So it does not necessarily need to be related to the actual spin of a particle. And no, sorry, that was the wrong click. Yeah, so each of these atoms, I'll not talk too much about the choice. It's usually atoms that when they are ionized, they still have one, after ionization, they have one valence electron, which makes this scheme here usually a bit simpler and more useful to the spin physics that we want to do. There's, of course, very many levels, even many more than I'm showing here. But of those relevant to the experiment, we identify two levels that are in some sense quite isolated from the rest of the spectrum. So that you can say, if I prepare the system in this state or that state, then the physics will be such, and I'll keep it vague as that they will not usually interact with all the other levels. So there will not be lots of things going on unless I have a laser with which I excite certain transitions in here. So spin in this context just means there's two levels that are fairly isolated from the rest. And if I prepare the system in that state, it will usually stay there unless I do something with it on purpose. And no, this is we'll be getting much later. Right. So now I'm for the technical side, I'm switching back to the Blackboard for the Zoom stream. Do I have to wait or do I just continue? Okay, so because before there was a little bit of a okay, now we have these atoms lying there in their pancake-shaped geometry. Now, what is the strategy? As I mentioned to you, the distances are such that these atoms will not naturally interact with each other, but we need to do something. And the strategy will be to excite phonon modes of that crystal, like make that whole thing, the whole crystal vibrate. And I'll show you that these phonons will mediate interactions between atoms. And this already gives you a glimpse how it comes that we end up with long-range interactions. Because if you think of a phonon mode, which is usually spatially extended, then if we use that mode to mediate interactions between atoms there, say if you think of the what is called, I think is it the drumhead mode, like the zero mode of some oscillation, the whole thing oscillating like this, then you will have oscillations over the whole range of the system. And there might be other oscillations modes where they are a bit shorter, and we may get to something that is not alpha equals 0 in our notation, but something that is a bit shorter range. But this will be the idea. And this is what people started doing, because when you want to use something like this for quantum information purposes, you of course need interactions to have gates, quantum logical operations or whatever. So you need interactions. And people started with this idea of using phonons here. Now, how does this work? Okay, I'll keep it like very vague, that people use lasers to excite phonons. And now in the crystal, we'll have a Hamiltonian part of the phonons, which is just a sum over some. Well, these are just phonons in the momentum basis written here. And these phonon operators here, of course, can be written in terms of the xi and pi. So the phonons are lattice vibrations, and they will be in their momentum representation. It's what you have seen for the simple harmonic oscillators will just be proportional to xi minus ipi, essentially, and then we are in a Fourier basis here. But still, one of these AKs will depend on all the xi's and pi's, so on all the momentum and position operators of the atoms that are then vibrating. So we get some, through this here, we get some spatial dependence into the system, which is what we want here. And the key idea now here is that phonons couple to the energy levels of atoms via what is called the AC Stark effect, or AC Stark shift, it's sometimes called. Let's use that word. It has another name also. What is it? Outler-Towns effect, which is pretty much the same thing. So the DC, like the regular Stark effect, you all know. This is splitting of levels in an electric field, which is it's the electric equivalent of the Zeeman effect in a magnetic field. This is something you all have certainly seen. And the AC version is for oscillating electric fields. And I'll just give you a brief sketch of what is done. So if you shine an oscillating electric field, like a laser, onto one of these atoms with the right choice of frequency, I'll come to the choice of frequency in a second, then say two levels, and these are the ones that we want to use for our qubit that are shown here. And I label them, say, as spin up and spin down for our spin bases. When shining, so with the AC Stark shift, what will happen is that there will, from the original levels, which were here, there will be a shift that the one is shifted upwards and the other is shifted downwards. So these two states will turn into they will be shifted. The upstate will be shifted up a little bit, and downstate will be shifted down a little bit. And the difference of the shift is proportional to the electrical field modulus squared divided by the detuning. And the detuning is the driving frequency of the laser that is being used is not exactly that frequency, but will differ by this delta here. So this here will be the driving frequency. Of the laser that is that we shine onto these atoms here. By doing this, we will shift the levels by a little bit. And in these shifted levels now, the shift will depend on E of X. So it's dependent on the space. So this is again the whole idea of the whole thing. We want to get a spatial dependence into the energies that we have. And the spatial dependence we will affect by the phonons when making the whole thing oscillate. This is how we create interactions in a system that before did not interact. Yeah, so you might get a position dependent energy shift. So H interacting is, well, some constant, which I will not really specify. And then the field strength, as is written here, xi modulus squared. And as I try to explain with this sketch, this will couple in that way to the sigma, to the z component of this sigma I. So the z component is the one for which this up and down is the spin eigenbasis. Right, this is what we get by shining a laser onto these atoms. And then we want to keep things simple and say, well, in linear approximation, we can say this term linearly is proportional to G xi of sigma iz. So whatever that exactly is, we'll say the linear term will be the one that we're looking at. And now I'm writing the x again in the phonon basis to have the same operators as we have up here. And then we get as a Hamiltonian sum of J. Coupling constants, which I don't specify here. I'll discuss them a bit later on. And then we have AK dagger plus AK and sigma iz. So what has happened here? I have replaced this xi by the phonon operators, which is pretty much this an expression like this, but for the AI, for the creation operators in real space. And then I've also done a Fourier transformation, which gives me different exponents and gives rise to these phonon operators here. Sorry? Yes. Yeah. Thank you. All right, so now we have the Hamiltonian that will lead us to the physics that we want to understand. So we now have the total Hamiltonian is the phonon part, which I've written up here, plus that interaction part. Yeah, let me just. write it down once more. I set h bar to 1 now to not have this constant lying around here. So what we have here is a spin-phonon interaction. What we set out to, or what we were hoping to get, is a spin-spin interaction. How do we get from this here to the spin-spin interaction? Well, we have the chance of doing of transforming this Hamiltonian by a unitary transformation to a different basis, such that we see in the Hamiltonian clearly the effective spin-spin interaction. So there's now a trick coming in, which I believe can be, it has been used in many different fields, so it's not specific to this topic here, which I think can be quite useful. We don't have much more time, but let's see if we can get this done. And it's called a spin polaron transformation. And whenever you see such a solving by transformation, there's always the question, well, how do I come up with the idea of exactly that transformation? And there's no good answer to this. I mean, I think these of course, at some point, people have experience with objects looking similar to that. But when, for the first time, someone came up with that, I think it involves staring at some equation for days and trying out certain things and coming up with that, with the right transformation. I don't think there's a really systematic way of saying, looking at this, you come up with that idea. So I'll just write down the transformation for you. So this is the unitary transformation that we want to use here. And I think in retrospect, when it's written, then one can kind of trace back where everything comes from. Yeah, this looks, of course, quite similar to the interaction term that we have over here. But yeah, so the interesting part is now that what we do is we want to transform the Hamiltonian. So we want to do something like we want to calculate something like U dagger HU. But to do this, to do this, we do separately the terms that we have. So let's do the phonon term here. So we do U dagger H phonon U. And we can, of course, pull this U in here. And I mean, now at some point you just have to go through the math of doing this. It's really not too complicated. And I'll tell you that when calculating this here, what you get is you will reproduce exactly the phonon term. So you'll get exactly what you started out with before the transformation, plus a very interesting term, ijk, which has a number of prefactors, gki, J divided by omega K, and then sigma I Z sigma J Z. We're not yet done. Minus H interaction again. So applying this transformation to the phononic part, we reproduce the phononic Hamiltonian. We obtain minus the interaction Hamiltonian, which is a good sign because we want to get rid of it. Maybe this minus is helping us, but of course we still have to transform the other part as well. And we have a part here that, apart from some coefficients, contains a spin-spin interaction. So we're not yet done. We have to see that the rest also works out nicely, but we have already the type of spin-spin interaction that we are hoping to get by this transformation. And yeah, so last line, and then I'm done for today. We have to do the same thing for the interaction Hamiltonian. So calculate U dagger interaction part and U, and we are reproducing again the interaction part, which is amazing because it will cancel with the minus interaction that we have up here. And we get another term that is minus 2 times I J K, and then we have G K I G K J divided by omega K, and again the sigma I Z sigma J Z part. Yeah, so it's really great how terms cancel that we did not like to have. And let's write down our final result here. And then, so the total Hamiltonian in the transformed form now is the phononic part minus, and then I'll use a shorter version of writing Jij sigma I sigma J. So starting out with the non-interacting atoms there, we first excite phonons in the system. Then we shine lasers onto the ions such that we have this AC Stark shift, such that the phonons will couple to the two-level system. And with this coupling, we end up with a Hamiltonian that, well, still has phonons, but otherwise is described by an effective spin-spin interaction that we have achieved in this way. And as a very last comment for today, then by some other technique that I will not go into, one can also, if one want to, create another term in the Hamiltonian that has the form of a magnetic field. Oh, sorry, that's here missing. For example, a transverse field or something similar. This is not covered by what I've explained to you, and I also not going to, because it's not a long range thing. It's something that routinely people do in these labs by shining microwave radiation onto the atoms, and it will do that, but I'll not mention it. So we have created a spin-spin interaction Hamiltonian, and in tomorrow's lecture, I will continue from here, showing you that this indeed turns out to be a long range interaction, which I haven't discussed so far. And when we have established this, then we can go on to equilibrium and non-equilibrium physics of such long-range systems, which will be the remaining topic of the lectures. Any questions? Yes, please.
Delta and the driving frequency.
Yeah.
So how are actually they defined?
How the delta and the driving? So there's the difference between the. So we pick the two levels that correspond to the qubit. They are separate by a certain frequency or energy difference, and then the skep delta is so. And then I apply a driving frequency that is not exactly that frequency, but a little bit lower, and the delta is the difference between. Does it answer your question? Okay. Well, no, it's not on anymore. If you look at the shift that you get, then it contained 1 over delta. So if you want the shift of the levels to be large, you choose delta small. But it's one of the knobs that people have for tuning the strength of that interaction.
Driving frequency is not able to excite your head, right? So the excited because you have a data amount of this.
Sorry, it's a little bit smaller than the difference between the levels. Yes, yeah.
It means that it does not actually excite the attention.
Within that level, no, yeah.
So in finite Hamiltonian, there is no hopping; it's just interaction.
Yeah, but so. I mean, now we have a spin Hamiltonian where usually we say the spin degrees of freedoms are assigned to lattice sites and there's no hoppings really. I mean, you can map spin models onto hopping models in some way, but in that spin language, there's hopping is something for fermionic or bosonic lattice models. But here it's spin-spin interaction, and yeah, if you want a spin. So you really have to think of these. I mean, these A's, the phonons are different. They live on a different Hilbert space than these spins really do. So these are initially in the system. I have the phonons and the spins, say, living together, interacting. And in this language after the transformation, I have the phonon part, which is just free phonons, so it's really boring and doing nothing. And I have the spins, which are interacting among each others. Still, in the background, the physics is, of course, that the spins interact through the phonons in some way. But once it's written in that way, and this is unitarily equivalent to what we started out with, it's really the spins interacting and the phonons doing their thing, which is, yeah, being phonons. Not, I wouldn't call it hopping because it's diagonal in the.
So is it possible to introduce the sigma x kind of interaction without phonon factor?
Well, so this is a complicated question. So there is other, if you do things a bit differently with these ion trap settings, you can do XY models as well. So you can do other types of spin models. But with this setup and in this calculation, you get Ising type interaction out. And the other part is that you still, so at some point I did a linear approximation, which is never fully justified in a real experiment. So there's always higher order terms. And in reality, you will have still a remaining spin phonon interaction, which will mess up your dynamics after hopefully a long time scale, depending on the size of that perturbation. But this is what the experimentalists initially had. First, they learned how to reduce this to a level that you can do spin physics on a very long time scale, that you have a very good fidelity for that. But then also very recently, a few papers came up where people try to use these and say, well, but we can also say we have these interactions, and so we engineer a system of a different kind. Maybe we can do other interesting things with it. So it's looked into, but yeah, this is the simplest version that you can come up with here.
Like beyond which you're linear.
Oh, this. Well, the honest answer is I don't really know, but from working with these people, the experience is that for the types of protocols we discussed, where we can see interesting physics of a type that I'll show you later on, they can reach these timescales. But this, of course, depends always timescale related to the spin-spin interaction timescale, because you want your spin physics to be already, so you want, this here sets a timescale in some way. And this will give you the interesting, this timescale will set the interesting spin physics timescale. And you want your disturbing phonon spin effects to be on a much slower timescale than this. But I don't have an answer in numbers for that, but I have the answer in the sense that people manage to, so it's long enough that you can do some interesting things with it, but observing like thermalization on all timescales will certainly be a problem for these models. Yeah.
So maybe we can continue over the tea break.
Sure.
So let's thank Miguel for his lectures.